So today it's an important topic on this data flow in cyber physical systems. So what does it mean, data flow? And we will be seeing the experimentation part of it. So hereafter, all the units or all the modules that we are going to discuss, we are going to use the tool called as Ptolemy. Okay. It's a tool called as Ptolemy. So Ptolemy II. So this is what we are going to use. So it's a kind of a modeling tool for hybrid systems. Okay, so generally we prefer the modeling for CPS model. For this tool, we are going to see. So module 4, 5, 6, these three modules are defined using the book Ptolemy. So I'll just show you that as well. So this is the book. So system design, modeling and simulation using Ptolemy tool. So the entire book is written using this Ptolemy tool itself. So that's what we are going to see in this next few days. Okay. So in this here, we are having something called as data flow. So data flow modeling. So you might have heard about data flow modeling mainly whenever you do any projects. So they will be asking you on data flow. Data flow means how the data flow between multiple modules of the system. So let's say if you are using a Raspberry Pi based microcontroller system, so in Raspberry Pi, from the Raspberry Pi, how it goes to the memory, from the memory, how it goes to the IO devices. So from the IO devices, how the Raspberry Pi captures the sensor signal. So all these things you will be writing a data flow graph. So generally we call a DFG data flow graph. Here, how we are going to model this data flow. So that is what we are going to see. We'll see two examples also. Okay, so you just practice those examples as well after the session is over, and we might include that in the laboratory also. Or let's see how that thing will work out. We'll see. Okay, so before that, first let me explain you some basic for a few slides are there. We'll explain you, and after that we'll come to the experimentation, how to do that. Okay, so data flow domains. Generally, they are called as pipe and filter design. So pipe and filter. So pipe and filter means the connection between actor or analogous to pipes that carry flows. So usually pipe will be carrying the flow of water or something between multiple actors. So in data flow design, each one who participate is called as an actor. So there will be multiple actors will be there. Between each and every actor, there will be a flow of data. So that will be called as pipes. Then the actors are analogous to filter the change of flows in some way. So change of flow in some way means, so once the data goes to one actor, according to the specification of the actor, the flow might be changed. Okay, the flow might be changed. So that we will see how the flow is getting changed. Okay, so analog to digital converter. So if the flow comes in analog format and the input, in the output, it will be changed to a digital format. If unsampled signal comes into a sample and hold circuit, the output will be the sampled signal comes out of the sample and hold circuit. So all these things are actors of a system. So similarly here, the data flow domains have pipes and filters. Generally in data flow design, what happens is in data flow, they often ignore timing. So there will be no timing there. If timing is not there, otherwise they go for uniformly spaced time between the actors. So that means they feel that the timing signal will be uniformly placed across the multiple actors. So one method is they don't have time. Other method is even if they have time, the time will be distributed equally among all the actors. So that's how the way the data flow domains works. So the first level of data flow domain is called as SDF, Synchronous Data Flow, otherwise called as static data flow. Okay. So please remember the synchronous data flow is pertaining to Ptolemy II, and the same synchronous data flow might be different for some other topic you have studied. You might study in embedded systems or other places. But this SDF, what we call, is only relevant to CPS and Ptolemy. So this Ptolemy II, this is relevant. And synchronous data flow is called as static data flow, and we have dynamic data flow also. So now we are going to see only the static data flow here. Okay. So in the static data flow, an actor begin execution when the required data inputs is available. So generally the actors fired to activate. So it start execution means it will be fired. So whenever there's an input at the particular input port, the actors fired. So to produce some outputs. It's relatively simple data flow. The actors are executed statically. That does not depend on the data process. That is the value of tokens that are passed between the actors. So generally statical flow means the value of the tokens that are passed between the actors doesn't bother. So whatever at the input, whatever I am having it, accordingly I can able to process it. That is static data flow. If the value of tokens, whatever coming in between the pipes, if that also affects, then we call that as a dynamic data flow. That will come later. Okay. So static data flow says that is statically executed means that does not depends on the data processing, which is in the pipes. Okay, between the actors. So in homogeneous SDF model, an actor fires when there is a token on each of the input port and produces a token on each output port. So generally, there will be a token at the input port and there will be a token at the output port. Not all actors produces and consume a single token each time they are fired. However, some requires multiple input tokens before they can be fired and produces multiple output tokens. So in this case, we have SISO, MISO, MIMO, and SIMO. So we have multiple things here. So single input, single output. Single output. So here is the multi-input, single output. Then multi-input, multi-output. Multi-output. So single input, multi-output. So these are the different models available. So here similarly here single input token and produces single output token. Multi-input token produces single output token. Then multi-input token produces multi-output tokens, and single input token produces multi-output tokens. So that's how the way this homogeneous SDF model plays a role. So you may not think that there will be only one token and there will be only one output token. It's not like that. So there will be multiple tokens. Okay. One example here, this example we will replicate. Okay. So this example says that a multi-rate SDF model. So a multi-rate SDF model, the spectrum actor requires 256 tokens to fire. So spectrum means this is a spectrum. So you can see the yellow color box here. This is a spectrum. This actor requires 256 tokens to fire. So one iteration of this model requires one iteration means one time when it want to produce, it has to produce 256 firings of sine wave, channel, and sequence plotter. So sine wave, channel, and sequence plotter. So that means based on this 256 tokens at the input, the spectrum get fired. Okay, so that is how the way these actors in the system or the data flow domain it work out in cyber physical systems. Okay, now when the order parameter is set to 8, so in the spectrum and the order is set to 8, the spectrum actor requires 2 power 8 input samples to fire, produces 2 power 8 output samples. Actually, the cap symbol is not displaying in the property here. So I have just used a cap symbol here. Actually, 2 power 8 means this is the cap symbol. 2 power 8 means totally 256 input samples. In order for the spectrum actor to fire once, the actors that supply its input data, sine wave and channel must each fire 256 times. So each of those have to fire 256 times, but the spectrum will be firing only one firing of spectrum. You can see that the SDF director means the synchronous data flow director extracts this relationship and defines one iteration of the model to consist of 256 firings of sine wave, channel, and sequence plotter, and one firing of spectrum. So one firing of spectrum have to be happened. Okay. Now this example we will see how we can able to do this example. Okay. So we are going to use Ptolemy software. So the name of the software is Ptolemy II, and then it is based on Java based software. It is on Java based software. So you need to have JDK 8 or JDK 8 to install this software. One of the powerful software CPS, Hyper Physical Systems. Okay. So it provides various options. I'll just show you two applications today. So first thing, I'm just opening the software. So to open the software, how to use this software. Okay, so number one is open a command prompt. Number two, CD this. Number three, open the folder and execute virgil.exe. So this is the software that we are going to execute. Okay, now I'm going to open the command prompt. Now this is the command prompt. So C colon uses TS Pradeep. So CD slash. Once you're done, we'll get C colon. So C Ptolemy. So that's a folder called Ptolemy. DAR. There is one more folder, Ptolemy II 11.0.1. Okay. So the name is says Ptolemy II 11.0.1 is the name of the version software. Okay. Now I use the DAR. So DAR it shows so many things. Let me use DAR star.exe. Now it will show you all the executable files in this. So in this Cape code, histogram, hypervisual, ptbook, ptiny, ptplot, and Virgil. So I'm going to use the software called as Virgil. So we need Cape code also. So Cape code we have already seen the other day how we can use Cape code in the module number 3. I think we have done it. Anyway, we will be seeing in the laboratory also. Now we have to use the software called as Virgil. So in Linux and Mac OS, you have to use Virgil like this /Virgil. But in Windows, you need not directly, you can right away, you can use virgil.exe. So once you do that, a software gets opened. A Java based software. Okay, so this window gets opened. Okay, now I'm going to create a new file. So file new. There are multiple models there, graph editor, icon editor, FSM editor, model, Pitera model transformation. There are so many things there. The first thing being the graph editor. We'll use graph editor. Okay, so I'll write down there. So now after this command, you can use C colon TOLEMY/PT to 11.0.1. Then use virgil.exe. Next thing is click new graph editor. Okay, so that's what we have done now. So a graph editor, we have opened it. So now first thing is the components to be added. Components to be added. So please listen carefully about this because the entire 4 modules, whatever we are going to learn, everything through practical examples only. Okay. So the theoretical concepts are less, only the practical components are involved. So based on the practical understanding only, you have to write the explanation of the components. Okay. So that way you have to do. So please listen carefully. Okay. Yes, someone asked in the Teams saying that, sir, what is the question format that we can expect tomorrow? Someone asked a question in Teams. We have discussed one full class for the questionnaires. Okay, so how the question can look like, we have already discussed also. So please remember, either you follow the video, what is been there in the Teams, download the video and then keep it, or else understand the class lecture to the core so that you can easily understand it. Okay, so components to be added. So we are going to components. So first thing is the director. The director to be added. So the name of the director is STF director. The STF director. Second component is sine wave. So sine wave to be added. So that will be on. There are two kinds of sine wave and triggered sine wave. There are two components, sine wave and triggered sine wave. We are going to have only sine wave. Okay. So then I'll check it here. So we'll be using a channel here. I will tell you what is a channel. Then spectrum we need to add. Spectrum we need to add. Then we need to add sequence plotter. So sequence plotter. So we need to add these 4 components. Okay. Now the channel also we need to add. So the channel we have to add 2 components in the channel. So one component is Gaussian. The other component is add subtract. These 2 components will be added for this graph editor. Okay. So please remember the components to be added is these components to be added. First we'll add without channel, we'll do that. After that, I'll show you with the channel. Okay. So first thing let me add the director. So I opened the editor already here. So this is the editor. So in the director, you can see here, we have the director here. So in the left hand side, we have directors. So click it. There are multiple directors there in the green color. So we have SDF. Just drag and drop it. So drag and drop SDF. Okay. So drag and drop SDF. So in case if you want to make it bigger, you click this icon. Okay. So if you want this icon, you can make it bigger and you can keep this. Okay. Now SDF director is synchronous data flow director. That's it. Now what is the next component? Sine wave we need to add. So in that case, so you need not go and search where the sine wave will be looking like. So just you can search it. Sine wave. I'm just searching it now. So since it is Java based software, sometimes the software will be slow. So now you can see we got something called as triggered sine wave. Okay, but we want only the sine wave. So sine wave is here. So sine wave is here. So drag and drop the sine wave. So sine wave. So you can see triggered sine wave. There are 2 differences. Triggered sine wave. See, I just open it. You can see triggered sine wave. There is one extra triggering here, but in the sine wave it is not there. So let us not go with the triggered sine. We are going for sine wave. Okay, so the sine wave, that is one. The next component is the spectrum. So I'll go with the spectrum. I'll go with the spectrum. So spectrum somewhere we got it now. So just remove it. And here is the spectrum. So just drag and drop the spectrum here. So the spectrum is next thing is sequence plotter. So sequence plotter. So sequence plotter is one of the plotting machine that we can plot using our. Okay. So now we got these 3 modules and we have a channel to be get ready now. Now first I will show you this example. After that we'll add the channel. Okay. Now once you have this ready, we have double click it. We'll show you the values. What is the sampling frequency? What is the frequency and what is the phase? So those things will be displayed here. Okay. Next thing is spectrum. So the order is 8. I told you 2 power 8 means 256 samples. 2 power 9 means 512 samples. 2 power 10 means 1024 sample, like that. It is in 2 powers. The power will be increasing. And sequence plotter. So this sequence plotter we are going to plot it. And it is only a graphing solution, so no need of any changing the value here. And synchronous director also we can change some of the values. So mostly iterations are automatic. In case if you feel unbounded iteration means it will keep on printing without any stoppage. Okay, so accordingly we have to adjust this director. So this entire application is monitored by the synchronous data flow director in this example. Okay, right. So now what we do is we have to attach it. So just drag and attach it here. So the sine wave is attached to spectrum and the spectrum is attached to sequence plot. Okay. So now I'll be, after I do this thing, in case if you want to check it, there's a play button here. So there's a play button here. Click this play button. So once you click the play button, you will get a curve like this. So this is the graph at the curve. Okay, so this is the graph. Okay, so in this graph, you can see here, starting from 0, ending at 2.56 somewhere here. So totally 2 power 8 samples. So totally the firings are 2 power 8. That means totally 256 firings in this example. Okay, now I'll be changing the spectrum value to 10. So 10 means commit. After 10, you just give this commit statement. Now I'll run it again. Now in this case, you can see 1024. You can see 1.0024. So somewhere here, the waveform is pointing out here. So 1.00, and this is the waveform for what the spectrum for the sinusoidal waveform. So this is what we got in the sinusoidal waveform. Similarly, I'll use 16 here. 16 means 65,536. So now you can see 65536. So somewhere here is coming. Okay. Now let me use 20. Use 20. So once you use 20 here, I don't know whether it executes. Let's see. Sometimes it is out of the bound means it won't be printing it, or it might be keep throwing some error. Okay, but 20 is also been printed here. So 20 2 power 20 will be such a huge value, maybe somewhere. I'm not sure what is the exact value we'll be getting 2 power 20. So that much value you are just getting it here. So here 2 power 20.
So 1048576.
Oh, fine. That means the value is right. 1048. The value is correct. Fine. So that way you can it will be showing. But anyway, I'll just show you the error also. What error you might encounter. So let me use 30 or something. I'll use it. Commit here. Now you can say that Java heap space. So uncaught exception. So the dismiss or display stack trace. So it will show you what error it is. So the heap memory could not able to store this value. This 30. So that's why 30 will not be accountable. So anyway, our value is 8 here. So that's okay. So 256 samples. Okay. So that is what here mentioned here in this slide here. When the order parameter is set to 8, the spectrum actor requires 2 power 8 input samples to fire and produces 2 power 8 output samples. In order for the spectrum actor to fire once, the actors that supplies input data, sine wave and channel must each fire 256 times. So the spectrum is going to fire only once for one iteration, but the other components involved in this process, they have to fire 256 times. Every time the sine wave has to fire first sample, second, third, 4, 5, 6 like that, 256 times it has to do. That's why for 2 power 20 it takes some time. Okay, because it has to process huge data. Okay, now we'll come to, I'll delete this again. This line around deleted. Then I will add one more thing called as Gaussian. Gaussian value. I add it here. This is the Gaussian value. Okay. Then we have to add subtract. We have add subtract. So this add subtract, you can have it here. Okay. So the Gaussian and the add subtract. Okay. So now in the add subtract, I am going to give the signal here. So one signal is added to the application here. The sinusoidal wave is added. Along with it, the Gaussian signal also will be added here. Okay. So the Gaussian output is added here, and the sinusoidal wave both are going to get added into the signal here. Okay. Now this will be the add subtract output will be sent to the spectrum, but there is no subtraction. So subtraction is empty here. We are not going to subtract any signals. So now what we are doing is sinusoidal waveform and the Gaussian waveform, both we are just adding to the add subtractor, and then that will be sent to the input as a spectrum. Okay, that's what we are doing now. So sinusoidal waveform is one signal and Gaussian is another signal. So now in this case, there are two signals, sine wave and the Gaussian wave. Both are added and sent as an input to, sent as an input for. Okay, now that's the input for the spectrum. So now we can check it here. Now once we do this, now we run it here. Okay, so this is the waveform what we get. Okay, so this is how the way the waveform looks like for the both the sinusoidal as well as the Gaussian signal. So in the earlier case, we have only this. Anyway, I'll just run it again. Okay. So this is what we have used. Yes. Let me be smaller, okay, so that you can easily check the signal. Okay. So this is a sequence plotter. Now you can see 256 samples here, 0 to 256 samples. Still here it is maintaining the same sample because spectrum order is 8. Now let me make the spectrum order to 10. Submit. Now when I run it, now you can see still more the waveform is denser because it is 1024, but accordingly 1024 sample will be provided by the Gaussian also. The channel also will be providing 1024 samples, and I'll go with one more 12. Let me put 12 and commit. So it is 4096. So 4096 samples now. So the firing takes that way. Now I'll put 16. Let's say a very huge value here. Okay, so this is how the waveform works. So this way you can able to analyze the signal. Okay, so this is how the signal work out. Okay, so here in this system we have actors. So sine wave is an actor, Gaussian is an actor, add subtract is an actor, spectrum is an actor, and sequence plotter is an actor. So anyway, this is one example of how we can able to do the cyber physical system design in Ptolemy on a data flow domain, synchronous data flow. Okay. So, and again, we can add some parameters also. Maybe those things we will see during the laboratory classes, how to add a parameter. So we can have a noise power also here. So in the Gaussian, we can add a noise power. So when we adjust the noise power, we can able to induce noise into the system. That also we can add it. So those things we can do something in the laboratory. Okay. Now this example, you can practice it. So whatever I have just plotted here now, just using the components, I have just plotted everything here. So you also try by yourself. And before that, you need to install Ptolemy also. See, sometimes Ptolemy failed to install. But even if it failed to install, the Java application works fine. So in most of the cases, it failed in my case. But still, the virgil.exe, the capecode.exe, all these things works fine. Okay. So this is one example. Now I will show you another example on same spectrum, but on a two different time domain as well as a frequency domain. I'll show you that. Okay, this is an example. Okay, so now in this example, what I am going to do is I'm going to use my real mic. What I am going to talk. You can check my video as well. In the video, in the audio, what I'm going to use. So now what it do is there's an audio capture file. So there is a actor called as audio capture that captures the audio via the mic. So I have a microphone. You can see my video now. I have a microphone, headphone, a microphone attached to me. I'm just talking over that. And there's a chopper. So chopper means it chops the audio captured signal. From the output chopper, it divides into two different time domains. So one is time domain, another is frequency domain. So anything sent via the spectrum converted to a frequency domain, and without any spectrum, it is a time domain. So as we know that the entire world is divided into two domains. One is time domain, another is frequency domain. So why we went for frequency domain? The job of frequency domain is easier to handle. Frequency is easy to handle when compared to time, because time is, we cannot experience time. So one good example, let's say if I tell you an example, what it says is bats and listen. Okay. Okay. Okay, so you can say 3 to 10 megahertz. So let me take 3 to 10 megahertz in frequency domain. Okay, so 3 megahertz to 10 megahertz. Okay, so let me say if we convert that to time, so 1 by frequency is usually time. So 1 divided by 3, it is 0.33. So 0.333 into 10 power 10 power minus 6. The other one is 1 by 10 is 0.1. So 0.1 megahertz means into 10 power seconds. Okay, so 0.33 into 10 power minus 6 and 0.1 into 10 power minus 6. So we have this thing. So 0.333 microseconds and 0.1 microsecond. So this timing signal we can see the timing we understand. So most of the processors they use timings, okay, because the processors are very fast enough to handle, they use timings. But real world scenario, we cannot use such a small timing. We cannot use. We can able to experience 1 second, 2 seconds, but we cannot able to experience even milliseconds. But how come microseconds? The nanoseconds are there. That's why we go for another frequency, another domain called as frequency domain. Okay. Now in this example, we have two domains, both time domain as well as frequency domain. Okay. We have time domain as well as frequency. So anything goes via the spectrum. It has the order of spectrum. So based on the order of the spectrum, the domain convert to frequency domain, and they say array plotter 2, array plotter 1. Okay. Now let me run it. So now you can see when I talk, just see the screen now. When I talk over the time domain, this is a time domain signal. The bigger one is a time domain and smaller one is a frequency domain. So now you can see the oscillations are very high in the time domain, whereas the oscillations are normalized in the frequency domain. Just you can see that. So whatever I'm just talking here over the microphone, let me place the microphone close to my mouth. Okay, now it is close to my mouth. So whenever I'm just talking over that, the time domain is oscillating beyond the amplitude. Whereas in the frequency domain, it always within the amplitude, but it maintains the noise level to the less value. So one advantage being that frequency domain can be controlled easily, whereas time domain we cannot control that much easily. So there is this is one advantage of frequency domain. That's why people usually go for frequency domain. Okay. Now instead of talking, I'm going to whistle now. I'm going to whistle. Okay. Now just see the time domain signal. Okay. Now I'm just talking and whistling. Talking now, whistling now, talking now. What could you observe on this whistling and the talk? Can anybody tell me that? Anyone, please? While talking and whistling. Students, are you there?
Sure, it wasn't so clear to observe. Sir, I think the amplitude was lesser in case of whistling for the time domain.
No, just now I'm just talking. Okay, so see the left hand side signal. You can check the left hand side signal. The talking is the waveform is too struggling. I mean, it's going away from the amplitude. But when I whistle, see that whistling.
Smooth.
Can you see the difference in whistling?
Yes, it's smoother.
Yes, it is smoother. The reason being, whistling is a perfect sinusoidal waveform. That's why people usually tell that the sound of a cuckoo bird, the cuckoo bird every day morning when it comes and it just sings, it is a perfect sinusoidal waveform. So even whistling also is a perfect sinusoidal, but when we talk over it, it is not a perfect sinusoidal waveform. So sinusoidal waveform on a time domain. So usually because we have 0 degree, 30 degree, 60 degree, 90 degree, then 120, 150 like that, it's a perfect sinusoidal waveform. So that's why when I talk over it, my voice modulates. So according to the modulation, the timing signal also adjusted and it crosses the amplitude sometimes. But now, see nowhere it has just distorted waveform. We didn't get it. You get the perfect smooth waveform. So that is what this time domain and the frequency domain of applications. Okay, I'll just come back to our topic here. So this example, I'll just give you this file also. You can try out from your machine as well. So first you can install Ptolemy. Then after that you can able to. Anyway, this week laboratory we are going to use Ptolemy only. I'll give some 4-5 exercises on Ptolemy. We will start using those things. Okay. So this kind of applications we call it as static data flow. So one application I would like to tell you. So that that's why I just brought this waveform so that we use the real world device. Okay, now in this case, so how the device is programmed, so how it can capture my microphone. So in that case, so select on any actor, right click, open actor. So there is an option open actor. So once you see the open actor, it shows you the source code of Java. So actually this is the Java source code. Okay, so this is a Java source code. So this source code will tell you how to read from a microphone of your computer which is attached to the computer. Similarly, right click chopper. So this chop open actor or press Ctrl L. So whichever case. And for example, if you take spectrum, right click and open actor. The spectrum is again designed using multiple actors. The spectrum is not a single component. It is also a component of, it's a composite actor. Composite actor means it has many other components. Now we can see it has a sequence, it has a multiplication division, it has a multiplication signal. Then we have a Fourier transform here, fast Fourier transform FFT. Then we have absolute value here. So whatever you give in modulo, it will be converted. Negative value also will be converted to positive. Then there's a scaling factor. Then decibels. Then finally we have the output. So this is how the way the spectrum works. Okay. Now in case if you want to see how the decibel works, right click open actor. Now here it will be showing you how a model looks like. So like that, for each and every actor, there is a Java code implemented and it is running in the backend. So this is how the way that entire Ptolemy was designed. So it is one of the powerful software. I don't know why this is not so popular, this software, but why people relying on MATLAB and other things. So maybe cyber physical system. That's why we have this software. It's ready. So what I do is during the lab class, I'll bring it some of the experiment that you can able to do by yourself. Just only drag and drop. So we have only designing. So we are not going to do any coding here. But the advanced level is you can able to write your own Java codes, understanding the Java APIs, write your source code, then develop design your applications. But our subject is on design aspects, so we will restrict ourselves to design aspect itself. Okay. So this is what the code of spectrum. So in case of maybe I'll see our own example what we have checked it. Now here add subtract, right click open actor. So this also a simple code for adding and subtraction the signal. Then sequence plotter, right click open actor. So likewise it will be showing you how the Java code is implemented. So if you want to check out also you can able to check out how the sequence plotter has been programmed and how the Gaussian is programmed. So how the Gaussian is programmed. So this way we can able to design our own actors. So this together we call it as the channel. In the book example where we have seen these two together called as the channel example. So this is a channel. Okay. So this is the basics of the SDF synchronous data flow director. So we have other things also in our system. We will see one by one. So we will see many applications possible in CPS system design. In case if you want to do a project, if you want to do some mini project, or if you want to do some kind of applications here, you can able to use Ptolemy II for demonstrating it. So the real world application. So you can see that I can use a mic. The other day I showed you I can able to scan a QR code right away from it, and then I can able to do things. So likewise, we use many applications on this tool. Okay. So any doubts, students?